Good. Okay. All right. So today I'm mostly just here to advertise a community engagement opportunity for the Nancy Grace Roman coronagraph instrument. There we go. All right, so the coronagraph instrument, unlike the wide field instrument, is a technology demonstration rather than a main facility instrument. And this will be very beneficial in terms of technology demonstration for the Habitable Worlds Observatory. So it's a visible light, high contrast coronagraph in space with active wavefront control. Expected to launch sort of 2026, 2027, somewhere in that window, before sort of the habitable world's architectures are reviewed before the decadal survey. Our requirement is pretty loose. We have to hit 10 to the minus 7 flux ratio at 6 to 9 lambda over D. You can see on the right here, I'm showing you some results from TVAC testing, thermal vacuum testing, and between the two white annuli, that's our 6 to 9 lambda over D target range. So you can see that we have already achieved this. Now we just have to do it on sky. Our predicted performance is likely to be better than this criterion, like at least 4 times better. And we're very optimistic that we'll be able to do some exciting science and tech demo work with Roman. It was delivered to Goddard in May of 2024 and has already been implemented onto the telescope infrastructure. You can see those photos here. Guess which one is a professional and which one I took on my phone. Let's see, can you see my cursor? Yeah, so this is the coronagraph instrument. And this is a little later on in the development. So you see the secondary, the primary, the instrument. This is the wide field on the back. And then this giant thing is the electronics box. Our plans for Roman, we are given 90-day observation phase to be conducted within the first 18 months, both for science and technology demonstration. Roman is essentially overbuilt to hit our 10 to the minus 7 criterion. There's lots of different modes, and I'm highlighting the ones that will be offered as sort of a best effort basis here. Our primary mode is this narrow field imaging chronography mode at 575 nanometers, band 1. And then we'll also be able to do polarimetry here as a goal mode. We also have a couple of different spectroscopy wavelengths. This one here is highlighting the methane absorption band. And then on the right, we have the wide field imaging mode, again, both in imaging and polarimetry. And here we have a couple of filters. So this will work at the 575 nanometer band 1, but also at longer wavelengths at the 825 nanometer. So what can we do with this level of contrast? We can look at self-luminous giant planets in the optical. We can image giant planets in reflected light for the first time. And then lots of exciting debris disk and exozodi science. In terms of technology demonstrations, we can do higher order wavefront sensing and check the stability of that, especially in terms of different stellar properties, diameters, magnitudes, understand the impact of contrast performance over the lifetime of the observatory. How does Roman compare to current facilities? Right, so this plot is a bit out of date. It hasn't been updated from some of the information we have from TVAC, but you can see here our requirement, that's the 10 to the minus 7 level, compared to HST NICMOS, James Webb NIRCam, HST STIS, and some ground-based facilities like GPiosphere, LBT, etc. Over plotted, we have some different types of planets. These are known planets in the color here, and then RV reflected light planets down in the gray. So you can see that even only at our requirement level, we're doing better than we can currently do from state of the art from the ground. And if we actually hit some of our goal performance levels, we'll be down here able to get a couple of reflected light planets. And a lot of disk science as well. So lots of debris disk science here, but we'll also be able to reach down into the terrestrial zone for a handful of these and investigate the exozodiac content in the optical, which, as you may know, is a key source of uncertainty for habitable worlds. A typical observing scenario for Roman will use a PSF star to dig the dark hole down to the required contrast, and then it'll blink back and forth between that PSF reference star and a science target. These are pretty long observations to get the necessary contrast and the integration time on the science target that you want. I can go into this in much more detail if you're interested, but to help understand the goals of the community interest survey that I'm going to speak about in a moment, it's useful to have some context. So as an example, for a VMAG of 5 star, you'll observe the reference star, which will be even brighter than a VMAG of 3, and the science target alternating, and 2 rolls for both cases. And in band 1, in the main imaging mode, you get about 14 hours of integration time on a science target per 24 hours. All right, and then one last piece of context. So because this isn't a main facility instrument, the structure of the science team looks a bit different. So for the coronagraph, a NASA Roses call put out in 2022 elicited PIs. There are 7 of us, and we're sort of tasked with developing all the infrastructure and the science program for the coronagraph. So there are 7 US PIs. We also have many international members, and then lots of folks working to achieve these goals. So the main takeaway here, one of the directives of the community participation program is to solicit community input. So we have 90 days of time within the first 18 months of the mission. What should we do with that time? Assuming we hit our 10⁻⁷ goal early on, what is your favorite science that you think we should do with a coronagraph? What technology demonstration aspects should we explore? We want to hear from the community. In order to make this as accessible as possible, we've put together a CGI primer that details a lot of the information I've just presented on the capabilities, the observing scenarios, etc., for the coronagraph. You can access the primer through that QR code. It's also linked directly from the survey. So what's included in the survey? So we focus on the modes I've described, the 2 imaging modes and the spectroscopy modes, which are provided as on a best effort basis. We ask you to rank various observing programs, both keyed towards the science goals and the technology demonstration goals. And there's also short answer questions that allow you to plug in additional information on your priorities, your favorite targets. This is pretty open form. And at the end, we'll ask for demographic information to make sure we're really sampling a representative community group. Questions we often get asked about the survey is who should fill this out? Everyone. If you have any interest in high contrast imaging for the next 50 years, you should fill out this survey because it's going to have far-reaching impacts on habitable worlds architectures. And particularly for early career researchers, you know, it's not going to be the people who are currently professors doing a bulk of this work, right? It's going to be you guys leading these science programs for habitable worlds. So please fill it out, send it to all of your friends and colleagues. We want as much information as possible. It's designed to be pretty quick, less than 10 minutes, a bit more if you want to educate yourself more in depth on Roman. And this isn't going to be the last opportunity for community feedback. We'll be doing a white paper call in the summer for longer form feedback and more detailed community input. Please take the survey, and I'm happy to answer any questions about the survey, about the coronagraph, anything you'd like. Thanks. Yeah.
It's a 10.7 country. I think you said it was easy, and I was wondering, like, is it just not having an atmosphere that makes it easy compared to ground-based?
Well, I mean, that's a big part of it. Our coronagraphs do a lot of the light suppression. This is the first time you get active wavefront control in space, and those two things are a powerful combination.
So you feel pretty confident about achieving that goal?
Yeah, I mean, from thermal vacuum testing alone, we were doing significantly better. And I forgot to mention, but those plots I showed with the contrast, those shouldn't represent a floor in our ability. We just sort of ran out of time to continue to dig the dark hole deeper. So.
I'm actually curious about what is the minimum separation or the angle that could be used to trace with the coronagraph? Because you mentioned that the debris disk size could be done with that.
Yes. So 0.14 arc seconds for our band one. The resolution isn't excellent. It's like an R50 or something like that. You can see a little grainy, but I hope that gives you a slightly better idea.
So the blue line here is the
blue line would be, yeah, the Roman spectral resolutions.
So all the images you shown here are just the synthetic images that made with the like the predicted images.
Yes.
Is there any other questions?
I wonder if there will be some Roman specific observers lunch talk or something like that to get to talk about community as general question. Will there be anything in Steward?
So we had a splinter session at the AAS. I don't currently have any other plans for advertisement for this survey. There will be a series of town halls that are associated with the white paper call later on this summer. But yeah, if you're interested in setting something up, if you think there's a quorum of people who'd be interested in learning more, I'm happy to do that.
Yeah, I'm also interested in the galactic plane survey. So there are a couple of others, and so I was wondering if there will be any town hall in Steward in the future.
Okay. So for the wide field instruments, I'm less clued in. But I know for the big core community surveys, there's a Roman mailing list that provides a lot of really useful information on a lot of online information sessions they've been having. But I don't know of anything happening in Steward in the near term.
Yeah, thanks. I can suggest that one to Observer's Lunch organizer.
Yeah.
Thank you.
There's any no other questions, I can move forward and yeah, I can do it. I'm on the list for the next one. So share the screen. So hello everyone, I'm Dingshan. Today I'm going to introduce the Python tool that I've been working on. And this is the tool that I developed together with Ilaria Pazzucucci and Ilaria's former student, Rachel Fernandez. Rachel now is a postdoc at the Pennsylvania State University. And this is basically a tool that we developed to help derive the stellar mass and the age from the isochrones. And we already put this software on GitHub, and it can be easily downloaded. And the main feature we provided here is basically, let me probably just share the screen to the GitHub page. And I can increase the font here. So the main purpose of this tool is to use this to handle different isochrones, especially for the young stellar objects. And then now currently we include the Baraf 2015 and Phaidon 2016 as well as the Parsec version 1.2 and 2.0 tracks. And in the future we can add more tracks. And this is basically using the Bayesian inference approach that many other people have been used in the literature. And we put this online because we've been in the Ilaria's 2016 work, we have used this tool. And there have been a lot of requests on asking us to help them to derive the stellar mass and ages using the same code that we used. And then we just decided to put this online so that this could be more helpful to the whole community. And we put this also on the PYPI as well now. So if you would like to try out this tool, you can simply just pipe install the YSL isochrone. And then we also provided a quick start guide as well as a lot of tutorial notebooks that you could refer to. And hopefully they could be useful. And so for a quick introductory of the installation, if you have never used the pipe install, pipe is basically a Python package that if you install Python from the Anaconda or other like packaging softwares, then you can just first upgrade the pipe to the latest version, and then you can use this line of code in your ZSH or in your bash, and then you can basically install that to your Python. And then what it can basically do is first of all, handle different isochrones and make a HR diagram like this. And it can also handle a large set of the data sets for different stars. And in this diagram here, we are combining the Phaidon and Baraf tracks. Phaidon is used for hotter stars, while the Baraf is used for the cooler ones, as the choice made in the literature, following earlier Ilaria's work and also Greg Herzig's works. And this is also the combination that was used in the Manara or PV7 chapter. So this is the simplest way we would like to present, and people can just use this to derive the whatever star they like for their stellar mass and age. And we also provide a function to plot this kind of the plots dividing into two different panels, because this is basically suggesting that we are using the Phaidon track for the hotter targets, which is larger, hotter than 3,900 Kelvin, and use the Baraf tracks for the cooler ones. And we can distinguish those targets here in different colors. And also we identify which are the stars are too faint or too bright, because for the stars that are too bright, they are basically younger, probably younger than the tracks we could provide, so that we need to assign the model age for them so that this tool can be used. And for the stars that are too faint, we're basically thinking it's because there are some like disk or envelope structure is hidden the stars there. So the stars is under luminous, so that we also need to assign some median age of the star forming region to those targets. And for all other targets, what we do is basically using the Bayesian framework method, as can be shown in this plot here. So we just calculate their likelihood function following some defined function in the literature, and then we find what is the maximum likelihood point to define what is the best fit age and mass. And in this method, we could also estimate what is the uncertainties from this method. And this software, as I showed earlier, is released now on the GitHub, and then you can just start playing with it using your favorite target samples. So I also would like to highlight the documentary that we recently prepared. So you can, if you go to the GitHub page, and then you can find there is a documentation here. And if you go there, we tried our best to prepare this documentation to help you use this software And first of all is the installation and also some other community guidelines and useful links, basically pointing you to other useful softwares also out there in the market. For example, you can use MEDIS if you don't have the effective temperature and the luminosity. And this is the tool that's focusing more on using the multi-wavelength photometric data and also using the extinction laws from the literature to handle those. And also there is isochromes as a Python package to handle the MIST, which is the MESA stellar evolutionary models. And there's a community tool provided in the Parsec website. And as our quick start guide, we have the tutorial notebooks on the GitHub, which is here. And it is also summarized in this documentation. And basically starting from the installation, and then import all the necessary packages you might be using in the end. And the software could help you download the tracks from the website, because we understand, especially for students who just started doing all this kind of research, it is quite hard to find different isochrome tracks and then handle all the data formats. So this is a very easy to use the definition in Python, and then you can just download the tracks and it will do all the formats you will need to do. And then just from there, you could test your input stellar temperature and the luminosity with their uncertainties, and then start plotting them on the HR diagram, just as I showed earlier, as well as using the style that is provided in the many other literature works, because blending those two tracks looks better or looks more beautiful, as many people think. And as well as plotting this likelihood function in this 2D scheme, and to derive what is the best fit agent mass. And as I said earlier, this package could also handle for the overluminous or underluminous targets by assuming its age. So it could only estimate the mass and age, assuming some other values. And this is plotting what is the 2D diagram of that likelihood function. And it can also handle a larger data set. For example, you can read it in a CSV file with the source information and the effective temperature as well as the luminosity. And then using that to derive to plot this kind of HR diagram with a lot of data sets, as well as the estimate mass and ages for this large data set, and then get what is the estimated mass and age in this output CSV. And then you can just do whatever research you would use after you obtain those parameters. And there are other methods, as I mentioned earlier. So for example, we implemented this closest grid point as on the isochrome instead of using the Bayesian framework, because this is the method that used in many literature works, but we still recommend people to use the Bayesian framework we provided, because that would give you the uncertainties. This method provided here is basically just for the sanity check and also to compare with the literature. And then we also provide a function assuming age to derive the stellar masses. So for this one, well, we just assume it's stellar age as the median age of that star forming region. And then we could just estimate the likelihood function just for the stellar mass. And you can get an estimate like this. And yeah, this is basically it. And in the future, if you want to use your own isochromes, we also provided a tutorial, and you can just create a matrix for yourself, and then just use whatever the stellar evolutionary models you want to use you like, and then you can get use this similar method to derive the stellar mass and age. And yeah, so this is basically what I would like to share today. It's not a very long presentation, but if you have any questions, feel free to bring it up. And also, if you have any feedback, comments, or suggestions, please contact me. And also, you can create some discussions or issues on the GitHub page that are all very welcomed. And yeah, and a little bit advertisement for myself. So I will be presenting in the Origin seminar, focusing on my other tool that I've been developing on the thermochemical disk models on the disk, protoplanetary disk. So stay tuned on that. I believe my talk will be on March. So yeah. Any questions related to this software or tool that I bring up here? Yes, Serena?
Yeah, just a quick question. I was also wondering why you're for the very low mass objects, is there a good reason why you're preferring, preferably using paraffin model? Because I think we found it for very low mass objects. Fiden's model also sometimes work. I mean, it worked much better for very low mass objects.
Okay, yeah, so in this package, actually, you can just specify which track you would like to use
Okay.
for your own research. And so that if you prefer Fiden, you can just use Fiden. So we choose the combination of Fiden and Baraf, especially use the Baraf for the cooler ones, just following the literature, as many other work has already used this combination.
Right.
Yeah.
Okay, thanks.
Of course.
March 24th.
Yeah, my talk will be on March 24th. Thank you, Alice. Yes.
Assuming that the input luminosity and temperature are Gaussian.
Yeah, it depends on which method you use to derive the uncertainties for them. But if you do not provide any uncertainties, we will just assume it's a Gaussian in log scale.
Also, you could provide a non.
Yeah, in the future you can provide but in the current version we just assume it's the prior we use is log uniform, so it's uniform in log. So we do not assume any priors for the mass and for those things, as well as we are assuming it's a Gaussian profile for the effective temperature and luminosity uncertainties. Maybe in the future we could add the function to just treat it slightly. So if there's no other questions, I will just stop sharing. Next, I think it's Griselda.
So, hi again. I'm Griselda, you can call me Gris. It's easier. Means the color gray in English. So here I'm going to try to summarize my work in a few points. But in simple words, my work has focused on one specific property, as I said, of molecular clouds, which is their angular momentum. More specifically, the angular momentum problem, or AMP, from a molecular cloud to core scales. So let's move to point 1. So what is the AMP? If we take a cloud, and if we suppose that it's under gravitational collapse to form just one single star, just collapsing monolithically to form just one single star, and if we suppose that the angular momentum is conserved, then the resultant star will rotate so fast that it will be destroyed. So we need to remove some angular momentum at some point to actually have stars. This IAMP can be seen in the famous JR relation of J plot. Okay, you can see my. So we have a specific angular momentum or a unit mass in y-axis versus radius or mass, it could be also the mass. And we collect a sample of different structures, clouds, clones, and cores. If the angular momentum is conserved, we will expect to see a constant line here, but what we observe is something like this. So we observe a trend, we have a positive slope, so that larger objects have more angular momentum per unit mass compared to the smaller one. So here at the bottom is a collection of different observational samples that we find in the literature, and we know that real J goes as a radius to the 1.5, 1.8, more or less. So back in the day when I first met my PhD supervisor, he told me, hey, I don't think this is due to gravitational terms, as some papers said, some famous papers said, as solution to the AMP. So we started to work on this. So if you look at the literature, you will find some possible solution, previous solutions to solve these AMP at these scales. So you could have magnetic braking, so magnetic fields, gravitational torques, gravity, turbulent viscosity, turbulence, or pressure gradient torques. So my work is focused on trying to figure out what is the main mechanism responsible to remove the angular momentum from molecular clouds at these scales. Which one is larger? Maybe there's a combination of a competition between these mechanisms. Maybe there's another one, we don't know. So that's the take-home message. I attack this problem using numerical simulations, most of them SDH simulations about the formation and collapse of giant molecular clouds in the warm neutral medium. So there are boxes of 256 parsecs per side, and we see how the cloud is assembled, how it's collapsing, it's fragmenting and forming stars. We can define here a numerical sample of clumps in different simulations. So we have simulations combining these three ingredients. So we have one simulation of gravity, then another simulation with gravity and turbulence, and then another simulation combining all the three. And then after defining a numerical sample of clumps using an algorithm based on density threshold, then we can start with the angular momentum in those clumps. So we can study these samples from 2 points of view. At fixed times, just take a few snapshots, define a numerical sample, and see what happens. And also taking advantage of using simulation, tracking those clumps from the past into the future to see how the angular momentum is evolving. At fixed times, of course, the first thing we wanted to test is if we recover the JR relation. So the answer is yes and no for some cases. So here in the plot on the right, you see, you see JR relation for one of our samples. The black line in both of those is the feed to the observations. In the red dashed line, it's the feed to our numerical sample. And you should say that, well, we are recovering the JR relation. But only if we restrict our sample to those clumps that have aspect ratios smaller than 3, so they are mostly roundish, which is consistent with what we see in the observational samples. We're talking mainly about dense cores. So when we restrict, then we recover the GR relation, and also we better recover the GR relation in those simulations that only contain turbulence and gravity and non-magnetic. Why non-magnetic field? So if we consider the full sample, which is on the left, if we consider the full sample, also elongated structures, those that are filaments here in the red square deviate from the observational trend. So the answer, if we recover this in my simulation, is yes, under certain conditions, but once we add filaments, then they deviate from the observational trend. So you can say that this GR relation is filaments. Now, in one of my simulations, when we have the 3 ingredients, we have magnetic fields, gravity, turbulence, we can actually measure the active torques in our clumps just to see which one is larger. So each torque is related to the one of possible solutions that I mentioned earlier. So we have pressure gradient torques here in orange, magnetic in green, gravitational, and hydrodynamic. The hydro torque is the one that includes turbulent viscosity. So here are the histograms of the magnitude for each torque, each clump, and they are just separated by the density threshold that was used to define the clump. So we are defining clumps at a density of the 300 particles per cubic centimeter up to 10 to the 5 particles per cubic centimeter. In the lower density threshold, which is the first histogram, they are like, we cannot distinguish between them. But as we increase and build dense structures, then we see how the hydro torque is mostly larger, and didn't happen in all my simulations. So the one that includes turbulent viscosity. So I think back in the 80s, the Larson relation proposed that as possible solution, the turbulent viscosity. But at that time, he discarded the idea because he thought that there were not enough turbulence in molecular clouds to maintain this mechanism. Now we know that molecular clouds are turbulent. So in my previous paper, we proposed a possible mechanism combining turbulent viscosity and gravity. So we're kind of trying to bring back this possible solution. And having the magnitude of the torque, which is now the largest compared to the other torques, kind of support that idea. Now, this is a big science, but we are using simulation, so we take advantage of the time. We can track clouds from the past into the future, and we can track them in two different ways. Once we define the cloud, we know how the particles, we know their ID, so we can plot the particles all with the same set of particles. We call this as tracking Lagrangian clouds, in the sense that we always following the same set of particles. And in tracking from the past, which is point 1, here at the bottom, we detect 2 periods of evolution of these clouds in the GR relation. So we observe an early period of evolution with a slope similar to that of the observations, and a late one when they are conserving. And in tracking those clouds to the future, no matter what density threshold we are using to define the clouds, we always see that some of the particles disperse and take away most of the angular momentum of the clouds, allowing the rest of the material to collapse. So we're seeing fragmentation by angular momentum observation. And this is similar to what happened in equation D. So the part that gains angular momentum moves upward, and the one that loses goes inward. So this is happening here, but in 3D, like in round geometry. So we are like putting a efficiency by angular momentum observation. We can lose like 60% of the material just because of that to just a few 5%, 10%. And finally, when we track these clouds, not always following the particles, the SPH particles, we apply the cloud finding algorithm at each time step. What we see is, even though we know that the clouds are collapsing, they tend to grow. So they move in the GR relation with a slope similar to that of the observations, but they're moving to larger radius. So the trend here is the clouds tend to grow even though they're collapsing. If you see always with the same threshold. So now that we have finally, my simulation had a lot of filaments. Right now I'm moving on because I'm trying to submit the paper soon. So I'm moving with filament formation. I'm interested in the 3D velocity field, the 3D magnetic field around filaments, the projections to look for rotation. So the filament is face on the third plot, the velocity decomposition in tangential and radial velocity components. In filaments, the rotation around some star particles, which is in the middle one, the 3D velocity field and 3D magnetic field at the bottom. So this is what we're doing right now. In my previous paper, the simulations analyzed did not have a lot of filaments, but now that I'm using another code and a lot of filaments, and we have deviation to the relations, so I'm interested in now filaments. And that's all. I can take questions.
Have any questions in the room or online?
So can I ask a question? How small structure can you actually follow with this filaments simulation?
Sorry, can you repeat the question?
Yeah, how small, what is the resolution of this So I'm wondering how small clumps you can actually follow.
The small,
Yeah, the scale.
Smallest, yeah,
Smallest.
scale.
Okay, they go like from 0.1 parsec, the smaller one, to some tens of parsecs. So we have some filaments like 30 parsecs long, and we have some small dense cores and clumps around the parsec.
Ask your question.
Well, I'm not all an expert here, so it's just hard. It's weird question, but I was just wondering if the magnetic field is external, like you put it in, or does it generate its own field?
I put in a uniform magnetic field at the beginning, then we apply some stirrants and turbulence. We can like vary the properties of the turbulence in terms of the modes, in terms of the amplitude, in terms of the energy. And at the end, the orientation is like self-consistent. This structure is.
Do you have any other questions? If no, we can move on for the next presentation.
I have a short introduction of what I'm doing now, and this is a little bit advertisement for my work. I mostly do chemistry in protoplanetary disks, and first, this is some introduction that what are protoplanetary disks? When like the molecular cloud collapse to form a star, because the conservation of angular momentum, it will rotate and form this kind of flat disk structure. And so this is what we believe planets form within. So this is class 2 disk is our focus. And to observe this kind of disks, we can use like SPITZR or JWST, the mid-infrared spectra, and we can trace the whole inner disk emission, including dust and gas. And if we see this kind of molecular lines, these are mostly tracing the molecular gas. And so why is this important? What can this kind of inner disk molecular composition tell us? First, this chemical abundance can be related to this inward pebble flux, that especially the amount of water within the inner disk, that you can see that the pebble drift rate can be related to this some of the parameters here. And this kind of inward pebble flux is also related to the size of formed planets. If we consider this pebble accretion forming scenario of planet formation, and also the inner disk composition is tightly related to the primordial composition of planets. Yeah. So what we do is mostly to fit and estimate the inner disk composition with these emission lines from our data. And for each set of parameters, we can have a simple LTE model for that molecule. And then we can fit the model with the data to get the fitted parameters for each molecule. And then for each molecule, the ratio of the abundance of them can tell us about the CTO ratios and also the inner disk chemical composition. Yeah. So this is an overview of how we do, how we study this data. And then this is one paper that I have published before, that special case of SC114. I just want to highlight that this one is a first and currently the only water-rich latent star disk, and also it has a very large disk. And we propose that this kind of behavior might be due to the large disk with substructures that can slow down but prolong the water-rich stage. Yeah, I was told that I only have 5 minutes, so I go through it very, very quickly. For more details, you can check my paper, or you can contact me with this. Maybe you can see it. This is my email address. Thank you very much.
Any questions for Chengyan?
So just a quick question. So therefore, it's a special case. It is special because of it's water, right? And
Yes.
I can see that, yeah, compared to the other two, the C2H2 HCN, there has a more HCN emission.
Yeah, because for other latent star disks, they are typically very rich in carbon, and it looks like that the HCN is also lower than C114.
Yeah. Okay, definitely should follow up with your paper. Thank you.
Is there any other data available for a younger and a late M-dwarf disk? Because the disk that the three comparison you are showing here seems like the SN114 is the youngest, and probably it's because it's younger, so it does have water.
Yes, this is also one of the reasons that why SC114 has so much water. And currently there are no published young latent star disk with JWST, but as far as I know, there will be one very soon that also has water.
Any other questions?
Just one more question. In order to have a lot of water in this very, very late type, I wonder if because they are, emission, right? Is that the temperature of the disk higher than the other? I mean, I'm just wondering what is making the abundant water in emission.
The temperature of the disk, we don't really have an estimate, but from the fitted temperature for the molecular lines, it is true that SC114 has a relatively higher temperature molecular emission than for the molecular gas. Yes.
Yeah, thank
Yeah,
you.
so
Thank you.
Yeah, that's also one of the explanations that why the water is strong, might be because that only relatively high temperature can activate this kind of water emission.
Right. Do you know what the other object is for the H2? Another water-rich late type object that JW is going to observe?
It's something JO4 something. I don't really remember.
Okay, thank you.
If there's no other questions, then thank you everyone for coming.
Oh,
and,
before that, I would like to I wrote next week's not tomorrow's Ilaria's talk.
Oh, yes.
Interesting, yeah.
Yeah, tomorrow's LTL's colloquium, Ilaria will introduce some interesting things about the JWST and the ALMA observations and the modelings for post-candidates. All right, so we'll see you guys next week, and the next week will be a presentation, I think. And we are going back to the normal origin seminar schedules.
Thank you.
Bye, thank you.